Hello, and thank you so much for coming to this presentation of a paper, The Adaptive Filtration for Respiratory Rate Detection. My name is Rob Ross, and I get to present this paper to you. While working on this paper, I got to work with an incredible group of collaborators. You'll see them listed there. They were members of the Drexel Wireless Systems Lab, and so thanks to them for this work as well. Let me start with a quick overview. So, in general, we're going to, the lab that I worked in focused on human biosignal sensing. So respiration is a piece of that, which is what we're going to talk about today, but it also would have to do with heart rate lots of other possible signals, whether that's thrombosis in the legs or uterine contraction. But for today, we're just going to talk about respiration rate. So we're going to start with proposing one way to detect respiration rate, which is a smart garment that we'll get to. But there are problems associated with that, and this paper in particular is presenting an approach for dealing with the signal denoising, so that's when we'll get into the meat of the paper. Then we'll talk about some of the results, and we'll conclude and talk about what comes next for the research group. So some motivation here. Respiration sensors are particularly noisy or particularly invasive. So respiration rate is an important signal for health. That seems pretty obvious. But many monitoring devices are invasive and limiting in other ways. So some devices are very invasive, like the device down here, which requires a mask. Sometimes it requires a patient being intubated. And then other devices don't require that level of invasion, but are surprisingly inaccurate. A paper that we cited in our paper noted that the best algorithm out of a set of hundreds of algorithms for detecting respiration rate was only 95% accurate, or 95% of the time within 4.5 or so breaths per minute. Which, if you think about what that means a person who's breathing at 8 breaths per minute, which is slow but appropriate, could appear to be breathing at 3 or 4 breaths per minute, which is dangerously low, or could appear to be breathing up at 8 or up at 12 or 13 breaths per minute. So there's a lot of variation here. And so what we believe we need is a more accurate, less invasive, and less limiting, that is physically limiting, requiring a patient to stay in one place, way of monitoring respiratory rate. So there are several devices that exist now that consist of some kind of smart garment, and you can see some of those devices here. But the question is how to smooth the signal that comes in from that. Now, other groups have used the music algorithm to denoise, and a key to that algorithm is that there are multiple interrogating antennas. As you'll see in a minute, what we're trying to do is get away from having multiple interrogating antennas or multiple of other sort of sources of truth. We'll get into that in a minute. Now, what our lab has developed is a smart garment that we call the Bellyband, and it uses a knitted yarn that is conductive or conductive, and we've developed a wireless antenna that reflects RF energy and then can tune or detune, go in or out of during respiratory movement. So basically, you've got some sort of interrogating antenna that pings the knit antenna on the Bellyband and gets back information from it. So here you can see a general setup where you've got a mannequin. This is a sort of animatronic robot that's getting pinged by an antenna here, and you can see some of the signal information coming back. So this signal has a lot of benefits. The antenna itself doesn't require power or wires, but there are some significant challenges that come with it. And those challenges include the signal being very quantized, that is, there's only a few values that it holds. The signal is subject to sort of perturbations like multipath and other problems that come from trying to pick up this signal wirelessly. And also the signal is just generally fairly noisy. So we can see an example of the signal here. And a question to think about is, how many breaths does this represent? And you can imagine that this could represent 2 breaths, or you can imagine that maybe it could represent 3 breaths, or maybe if the noise was loud enough, you could imagine this is actually just a flat line, no breaths at all. And the question is how to get that respiratory rate out. So in prior work, we've worked on a couple different ways of getting that signal out. One is to take multiple algorithms and apply expectation maximization to the result of those multiple algorithms. Another is to use multiple knit antennas. So you have on the person's body one knit antenna that's maybe close to where respiratory activity happens and one that's farther away. And so there's a couple different pieces there, but the challenge is that fusion algorithms, that is taking multiple algorithms and expectation maximizing over them, are computationally expensive. And we want this to run in real time. So if it's too expensive and is not able to run in real time, that's clearly a problem. You need to be able to ingest this on the fly. And also having multiple physical sensors is also expensive in other ways, right? So in this paper, we're seeking to not only improve on the accuracy of our prior work, but also use a single algorithm that can run in real time, use a single knit antenna, and use a single interrogator. So all 3 of those are improvements that this work covers. Now a little bit of background on smoothing algorithms. So a filtering algorithm, you can think of something like a rolling average or a moving average, can smooth quantized artifacts from a signal pretty well, but you need to be able to know the window size, that is the number of points to filter on. And if you set that number of points incorrectly, you will get an inappropriate smoothing of the signal. So here you can see a simple curve that has a constant frequency, and the rolling average was set appropriately, and so you get a really nice smoothed signal out, right? That's sort of the ideal world, and that's not the world that the sensor lives in. So we need to be able to do something a little bit more intelligent here. The approach that we used is called a Savitzky-Golay filter, and this filter was invented back in the 60s, so it's been around a while. It's very low cost, and it's low cost because it's basically just a matrix multiply of the set of points that come in, and that matrix is defined entirely outside of the points that come in. So it's a single set of values in that matrix that then hold throughout the entire measurement cycle. And so that can be computed ahead of time, and you're just doing a single matrix multiply each time. It's pretty cheap to do. So the Savitzky-Golay filter has 2 parameters. One parameter is the degree of the polynomial that it's going to try and fit to the points, and the other parameter we call n is the number of points that are being fit. And then what the filter does is it minimizes the least squares distance between that k degree polynomial and the set of n points. A specific example of a Savitzky-Golay filter is a moving average, which would be a Savitzky-Golay filter with a 0 degree polynomial and n points in it. So here's a visualization of what it's trying to do. It picks 1 point, it fits here a 2 degree polynomial to a set of 7 points, and then it resets this center point so that the least squares distance is minimized. Now we chose k to be 3, so that is a 3 degree polynomial, so that each iteration of the filter would contain both a peak and a trough, so we get 1 full respiration. And so you can see here a visualization. This is clearly not respiration rate. This is a different kind of visualization, but you can see how it's moving through with a 3 degree polynomial and filtering these points as it goes. And you'll notice that the polynomial changes each time, but its degree is the same each time. So the question is, back to respiration rate, how do we choose n? How do we choose the number of points? Now the problem is that no single value of n will correctly smooth the respiratory curve for all respiration rates. So what we see here is a patient who's breathing at 15 breaths per minute, and in the middle we are using 11 points in the Savitzky-Golay filter, so n equals 11, and smoothing that and then choosing how many breaths are. So each red dot is the maximum inhale, and each blue dot is the maximum exhale. So you can see this, each red-blue pairing is 1 breath, right? Now on the bottom, we put 51 points in as n, and you can see here a beautiful curve showing us what we want to see, right? So picking n is important. On the other side, here's a patient who's breathing at 70 breaths per minute, which is very elevated but still biologically possible. And in the middle, we've got these 51 points put in. So this is corresponding here, right? And you can see it finds an inappropriate number of breaths. And then if we pass in 11 points, then it catches the right number of breaths. So if you know ahead of time how many points to put in, you can smooth this easily. But of course, you can't know it ahead of time. If you knew it ahead of time, you'd already know the respiration rate. So how do we get that set value? That's the key. So our solution is to adapt n based upon the respiratory rate calculated in the previous window. So we'll show you what that looks like. So what you can imagine here, let's assume that we know the respiration rate at the current window. So I know that we don't understand how we're going to get there yet, but hold that for a minute. Assume that we know that value. And then we're going to recognize that the rest, so if we have a half-second window slide, so we're going to take the respiration rate take a window of maybe 15 seconds, detect the respiration rate for that window, slide over just a half a second so that 14.5 seconds overlap between the two tests, and take it again. And what we're going to assume, which holds, is that the respiratory rate at that half-second slid over window is close to our current respiratory rate. So there's not going to be a huge change from moment to moment. And this holds even if there's an instantaneous respiratory rate change of like 10 to 70, which would be enormous. Even then, because there's that slide over, the average respiratory rate over that window does not increase by very much. So we set the n in the next window to expect the respiratory rate of the current window. And then the system is then able to adjust, to make those small adjustments. If it assumes that the next respiratory rate is the same as the current, when it filters it based on that assumption, it actually calculates a respiratory rate that's accurate, so it can match those small changes. Now, how do you get n for the first window? That's the key. And the key is to bootstrap that value by setting the respiratory rate high at the beginning. Say the patient is breathing 120 breaths per minute, which is very, very high, perhaps biologically impossible. And then if you give a 20-second warm-up period, by the end of the 20 seconds, the system will converge down to hit the actual respiratory rate. So now we've got how to find the first time, how to set the first time, and we've got how to find each next window. Now there are times when the filter will disagree, or will sort of lose the signal. That doesn't happen often, but sometimes that happens. And if that happens, we can reinitialize the filter parameters back up to 120, say that we've got 20 seconds of warm-up, and then pick up the breath rate again. So we analyzed 25 respiratory scenarios from 2 different human subjects, and we hooked up the Bellyband and also hooked up a ground truth collection device with a Werner respiratory sensor, which was a wired sensor. And then we obtained an average root mean squared error of 4 breaths per minute over these trials. So here you can see an example. Here the patient's respiratory rate changes instantaneously, and the filter is able to pick that up well. Same story here. We've got a much faster change. So what you see here is the raw signal, and then the smooth signal, and then the smooth signal with the added peaks and valleys marked. So this algorithm, which performed 4.1 breaths per minute error, this algorithm required 67% less processing time than our previous best. So what that means is that now we're processing faster than real time, and it was 68% more accurate than our previous estimates. And again, this is the absolute accuracy. So where do we go from here? So what we've done is presented an adaptively parameterized Savitzky-Golay filter. So what we're doing is adapting n, that n value. And the way that it adapts it is by using the estimate of respiratory rate in the previous window to choose its parameters for the current window. And this approach enabled respiratory rate estimation with improved accuracy and improved runtime performance with one sensor, one interrogator, and only one algorithm in real time. So going forward in the future, we plan to expand our human trials with increased subject diversity. We only had 2 subjects in this case, and increased scenario diversity, different positions, that sort of thing. And we plan to integrate this work into an end-to-end system that's able to infer dangerous user states like sleep apnea, and also just detect regular respiratory rate. We'd like to thank our sponsors from the NSF and the NIH, and also the CURE grant in Pennsylvania. Without their financial support, the research would not have moved forward. And thank you for listening, and that's the end of the presentation.